Clustering can tell you which host looks structurally different from every other host in your environment. It can't tell you if a host that's always looked completely normal just quietly changed. Welcome back to Threat Hunting 201. This is episode 5, Anomaly Detection and Forecasting. Quick recap. Stacking ranks things by frequency, grouping pivots from one entity to everything connected to it, clustering profiles entities across multiple dimensions at once to find who's structurally different. All three of those are snapshots. They look at one moment in time and ask, who's the outlier right now? Anomaly detection and forecasting is different because it introduces time as an axis. Instead of comparing an entity to everyone else, you compare it to itself, its own baseline, its own history, and forecasting takes that one step further. Instead of just flagging this is different, you project where a metric is heading and catch it before it crosses a line. Here's the actual data from this episode's lab. One host sat at roughly one process launch a minute for about 8 minutes straight. Background noise, nothing interesting. Clustering would look at that host, compare it against every other host, and find nothing structurally unusual because one process a minute isn't unusual for anybody. Then that same host jumped to 22 processes in the next 60 seconds. Clustering still sees nothing new. Same host, same kind of commands, nothing to structurally set it apart from 100 other busy hosts. Anomaly detection catches it immediately because it's not comparing this host to everyone else. It's comparing this host to itself 60 seconds earlier. Peer comparison versus self-referential baseline. That's the whole difference. Let me just note this down because this table is the thing to remember from this whole episode. Stacking ranks, grouping pivots, clustering profiles across dimensions, and anomaly detection and forecasting baselines an entity against its own history and projects where it's headed. 4 completely different questions, and none of them replace each other. Here is a real gap. In this episode's lab data, a Windows host ran a quiet stretch of completely benign discovery commands, whomi, hostname, ipconfig, for about 10 minutes. Nothing about any single one of those commands is suspicious. Clustering would look at that host, compare it to every other host, and find nothing structurally unusual because none of it stands out on its own. Then the exact same host, in the space of about 90 seconds, ran 50 of those same commands back to back. Clustering again sees nothing new. It's the same commands, same host, nothing to structurally distinguish it from its own earlier behavior in a multi-dimensional sense. But the rate just changed by more than 20 times. That's the miss. So when do you actually reach for this? Whenever you have a metric that's expected to be stable for a given entity over time, process launch rate per host, login frequency per user, DNS query volume per host, and what matters isn't how does this compare to everyone else. It's how does this compare to what's normal for this one. If you're coming from Splunk, you've probably built this with stream stats, something like stream stats avg count as avg count dev count as dev count window equals 10, then an eval flagging anything more than 2 standard deviations out, or you've reached for the machine learning toolkit's anomaly detection command entirely. Here's the honest answer to a question I got asked directly while building this episode. Should this just be done in Splunk's ML Toolkit instead of Elastic? I tried both. The ML Toolkit's k-means style approach gives you an anomaly score you have to trust. The SQL version I'm about to show you gives you a threshold you can read out loud and defend to your SOC lead in one sentence. I'll show you exactly why that matters in a few minutes. Let's build these in Kibana. Quick note before we do, every hunt in this episode runs against real telemetry. But it's not telemetry I just happen to have lying around. I built a dedicated Caldera capability specifically to generate it, a baseline period of quiet, normal looking activity followed by a deliberate deviation compressed into one operation. Both the Caldera ability and the exact data set it produced are open source, links in the description. You can either pull my data set directly and follow along with the identical numbers I'm about to show you, or run the simulation yourself and generate your own. Either way, nothing in this episode is a black box. First hunt. Process volume baseline break. The hypothesis is simple. Pick a host, establish what its normal process creation rate looks like, then flag any minute where it blows past that rate. Could stacking find this? Stacking would rank host by total process count over the whole window. But a host that's quiet for 9 minutes and then spikes for 1 minute might still rank lower in total count than a host that's just moderately busy the entire time. Stacking would completely miss the spike because it's only looking at the total, not the shape of the activity over time. Could grouping find this? Grouping would happily pivot from a process to its host, or from a host to every process it launched. But it has no concept of rate and no concept of compared to when. It answers what's connected, not was this normal for this entity. This needs a real time bucketed baseline. Let's build it. Alright, I'm in Kibana, ESQL mode, discover. Let's start simple. From logs star, I want sysmon process creation events. So I'll add where winlog.event id equals 1. That's sysmon's process create event code. And host.name equals THOR-HQ windows. Let's run that first. Okay, this is every single process launch on this host across our whole window. Not useful yet on its own. I need to see this bucketed by time, not as one flat list. Let's add stats process count equals count star by bucket equals bucket of timestamp 1 minute. That groups every event into its own 1 minute window and counts how many processes fired inside it. Let's run it. Now look at this. Early buckets, 1 process a minute, 1, 1, 1. That's our baseline. Quiet, steady, boring. Then watch this bucket, 22, and the very next one, 9. From 1 to 22 in the space of a single minute. Now in a real production hunt, you wouldn't eyeball this. You'd add an explicit threshold. Let's do that. Eval baseline rate equals 1.0. Then eval is deviation equals process count greater than baseline.rate times 2. Run it, and there it is. Those two buckets flag true, everything else flags false. That's a self-referential baseline break, computed, not eyeballed. Second hunt. First seen suspicious pattern. Same lab, same host, but this time we're not looking at volume. We're looking for something that's never happened before. Now, could stacking find this? Stacking would rank every PowerShell launch on this host by frequency. And here's the problem. The one we actually care about only happens once. Frequency ranking treats happened once as the least interesting row in the table, not the most. Could clustering find this? Clustering might group command lines by similarity, but it still needs a human staring at the output to notice the one outlier cluster of size 1. It doesn't have a built-in notion of this exact pattern is new. What we actually need has this specific pattern, not PowerShell in general, the specific combination of an encoded command plus a hidden window ever shown up on this host before. That's a first scene check, and first scene is fundamentally a time question. Let's build it from log star, where host.name equals THOR-HQ windows and winlog.event id equals 1. Now I went PowerShell launches specifically, so and winlog.event data.image like star PowerShell.x. Let's run that. 6 results, all PowerShell. If I stopped here and just eyeballed 6 rows, sure, I might spot the odd one. But let's make the hunt actually prove it, not rely on me getting lucky. I'll add and winlog.event.data.command line like star dash encoded command star. That's the specific flag pattern I care about. Run it. 2 results now, not 1. That's the first gotcha worth showing you. One of these is the real encoded invocation, and the other is a false positive because a completely unrelated script on this host happened to mention the words encoded command as plain text inside its own logging output. This is exactly the kind of thing that bites you in a real hunt if you don't check your results against ground truth. So I tighten it, and not winlog.event data.command line like star argument list star. That excludes the false positives specific wrapper syntax. Run it again. 1 result, exactly 1. That's our real first seen encoded PowerShell invocation, cleanly isolated from 5 other plain boring launches in the same window. Third hunt, and this is the hardest one, DNS beacon forecast deviation. The setup: a host is making DNS queries to some random looking subdomains, which on its own isn't automatically malicious. DGA style domains show up in plenty of contexts. What matters here is the rate those queries are happening at and whether that rate is accelerating. Could any previous technique catch this? Stacking would rank domains or hosts by total query count, but a slow ramp from 1 query a minute to 4 queries a minute over 8 minutes might not even crack the top of a frequency list. Grouping would happily show you every domain a host queried, but has zero concept of the gap between these queries is shrinking. Clustering could group similar looking domain strings together, genuinely useful for spotting DGA patterns structurally, but it still can't tell you the beacon is speeding up. This is a trend. And ESQL, I'll be upfront, has no native forecasting function. So we're going to build the explainable version ourselves. From logs star, where host.name equals THOR-HQ windows and winlog.event IID equals 22. That's Sysman's DNS query event. Let's bucket this the same way we did in Hunt 5.1. Stats query chart count equals count star by bucket equals bucket of timestamp 1 minute. Run it. Look at this progression: 1 1 1 2 2 2 3 4. That's not noise, that's a clean accelerating ramp. Real beacon malware very often does exactly this. It starts slow and quiet to avoid tripping obvious volume alerts, then checks in more and more frequently as it approaches whatever it's actually waiting to do. Now let's make this a real hunt. Instead of just a chart I'm reading out loud, eval baseline rate equals 1.0. That's the rate we observed in the early quiet buckets. Then eval is deviation equals query count greater than baseline rate times 2. Run it. The last 2 buckets, 3 and 4 queries a minute, both flag true. Everything before that flags false. And here's the part that actually answers the Splunk ML Toolkit question from earlier. I could have handed this to a black box anomaly scoring model and gotten back a number I'd have to trust. Instead, I can tell you exactly why these 2 buckets are flagged. They're more than double the observed baseline rate. That's a sentence, not a black box. Let's talk about why that distinction matters. A black box model, Splunk's k-means style clustering or any off-the-shelf anomaly scorer, gives you an output, a score, a cluster ID, a probability. It doesn't give you a sentence you can put in a ticket. Every hunt in this episode ends in a plain English threshold more than double the baseline rate. First time this exact pattern has occurred, 22 processes where one was expected. Each of those is something you can defend to a SOC lead, an auditor, or your own future self at 2 a.m. rereading an old alert. Explainability is what makes a hunt something you can act on with confidence. Let's recap. Hunt 1. A host's process launcher rate broke its own baseline by more than 20 times, caught with a 1-line eval threshold. Hunt 2. 1 real encoded PowerShell invocation isolated from a false positive, and 5 boring launches using a first seen pattern check. Hunt 3. DNS beacons checking in frequency accelerating from once a minute to 4 times a minute. A forecast style deviation, fully explainable, no black box required. Everything you saw, the Caldera capability that generated this data and the exact data set itself is open source, linked below. Pull it, replay it, or run the simulation yourself. Next episode, we are moving into correlation and sequencing, chaining separate anomalies together into one attack timeline. If this helped, tell me on LinkedIn. I read every comment. Stay curious, keep hunting.